Hello developers, let's start developing. My name is Veko and today we're gonna take care, hopefully, of the ninth task of the Advent of Code for 2021. Let's see what we have in store today. These caves. Yeah, so there was a mention of caves in day 7 and day 8. And I expected to have to do something with a matrix that we will need to somehow manage, and seems today is the day we get to do that. Lava tubes. Okay, if you can model how the smoke flows through the cave, you might be able to avoid it and be that much safer. It's a height map of the floor of nearby caves for you. Smoke flows to the lowest point of the area it's in. For random comparison, the following height map. To the height of a particular location where 9 is the highest and 0 is the lowest. So all of the numbers will be between 0 and 9. To find the low points, the locations that are lower, so we need to find the local minimums, so to say. When a point when if you get to that point, you cannot get out of it without going up. Yeah? Okay. For adjustment points, 2 or 3. So we need to compare with the neighbors. I kinda hate this. I kinda hate processing grids when we have to process the neighbors all the time, because that tends to create some relatively ugly code, but that's just the way you need to do it. So we just need to take care of finding the low points. Yeah. Do we have... Yeah, we have situations like this. 8, 8. So that does not count as a low point, I think. Just let me check. The locations that are lower. So it's lower, not lower or equal than any of the adjustments locations. Okay, so let's start. Since we only have bolding, this is our input. So what we will need to do, we will need to read the input into a... It's not going to be a number array, it's going to be a number array, aka matrix. So we need to change number with another dimension. The result will be a number, the input is an array, the input is a matrix, and it's a matrix, so this needs to return a matrix, and an empty array is by definition an empty matrix. So we'll need to read the input lines, and we'll need to split them on an empty string and map them. It should have learned by now that I don't like using this kind of mapping using the number constructor. What I prefer is to use the parseInt function with a parameter of 10, because that's the radix. So each of the line is now mapped to an array of numbers. So yeah, that's the input. So because I kinda hate doing special cases for the corners, what I'm gonna do, let's do some Excel investigation. As I've mentioned, Excel is kinda okay when dealing with data, only I didn't want this to be treated as numbers. I will like this to be treated as text. So I will just format this cell, says that this is a text, and if this is a text, then I can use the text to column separator, and just say each of these is a column. Yeah. So we have these values. Let's spread them out just a bit more. And now I actually want them to be numbers. Let's see if this works. So this minus this is, yeah, they are numbers. What I will do, yeah, because right now if we want to check if this satisfies the conditions, we will have to say if this is bigger than this, and so actually we need to do it the other way around, and this is bigger than this is bigger than this, and this is bigger than this, and this is bigger than this. Actually we wanted the other way around, so we wanted that f4 is less than all of those items in order to have that. And we can actually scale this out for each of the items. Let's just add a few more rows. Yeah, this goes for that. So and you can see that for the 3 and for the 2 as well, we're actually checking empty cells. And you can see the 1, for the 1 we got the wrong answer, because 1 is counted to be bigger than this, and we actually don't need to take care of this. So what I would like to do, what happens if I say that this is a 99 and I stretch that 99 all around my initial matrix. Now I want it to be not 88, 99, 99. Excel is sometimes hard of hearing, as some people might say, but of course we can use any number including 10 and above. So if we start with this one and just take it over to here, we need one row more for the 0. This is for the 1, this is, and then we need one row more for the 0, and we got that the 0 is actually that kind of place. And we can even now use some good old conditional formatting that says format all cells based on the value, tape lowest value. Okay, we can use, oh, that didn't work. We can say color scale, or we can use, I think, icon sets actually. Nope, we're gonna need to create a custom rule format all search bells and then value. Format only cells that contain. If the same value is equal to true, format, where is the color, fill, green, okay, okay. Yay! Here we have the solutions, 1, 2, 3, 4. Let's see if that is, yeah, 1, 0, this 5 and the 5 at the bottom. This row is false positive because this row is about the nines. So for each of our cases we calculated whether it's the correct value. Now I want to do something like this algorithm as well in JavaScript, because you can see that this is a relatively simple formula and we are not checking whether that neighbor exists, and that is the part that always irks me. That's each time that I'm checking a cell I have to ask, but do you have a neighbor? So this way I ensure that the cells do have neighbors, and once I know that do, I just run it. So we will create another matrix that is an expanded matrix, and inside that matrix we will add an array of length the same as the row, the length of the first row, yep, and we're gonna fill it not with zeros, but we're gonna fill it with 99s, and we're gonna add just such an array at the end, and we're not gonna be, the length will not be the length of the original rows, but it will be bigger by 2, because here we have to take care of the corners as well. Technically we're not using these corners in none of our calculations, but it's better if they are there, everything looks kinda nicer. And then I'm gonna add the input, but the input, not the input itself, but an array that will have 99, then all the elements of the input, which is a matrix, so that's not gonna work. So I'm gonna map each row of the input to another row that is basically 99, then the row, and then 99 once more. And of course this will need to be deconstructed as well. And let's see if this thing works. I'm gonna print out this matrix, so we're gonna print out the expanded, and we're gonna do a cell processor. Well, basically if we have a number and that number is equal to 99, then print out an X. We don't need this or this or this. Print out an X, print out a dot actually, otherwise print out N. Let's see what we get. If my code is correct, we should get a our input nicely surrounded with dots. So you can see that we are reading the input, indeed we are reading the input correctly, and here is our output. Yeah, we have dots all over the place. So now we can run a simple for loop, nested for loop, because it's a matrix, so that we can detect that. So we can say for, and we're gonna start at 1. So this is gonna be the X, of course, this is gonna be the Y, and now everything is messed up. And so we're not gonna run our loop. Apparently somebody else did this kind of an algorithm because it detected what I wanted to do. We're not gonna run it from 0 up to the length. We're gonna run it from 1 up to the one before last. So we're not gonna check the last 99s. We know they're 99s because we put them there. And we're just gonna loop through it. We are using the same thing, expanded of x actually. So I will just rename this. This is row and this is call. I kind of think better in this way. So, or even index and index. I like these names better because now I can do this. Row is expanded of index, of row index. So we're not running through an array within an array within an array. We're just managing some single length arrays, single index arrays. So we need to check whether our neighbors are bigger than us. And the total value, we need to map up the risk levels, and risk levels is 1 plus its height. So we need to detect if it's a risk level. So if, you saw that I'm not stingy with variable names, so I will add a few. So the cell value is the row of the column index. The top one, the one that's right above us will always be, this one. The one to the left will be this one. The bottom will be one index more, and the right will be one index to the right. Of course, we don't have to check whether these indices actually exist because we made sure with this. And now we can add some code. So if top is less than the cell, less than or equal of the cell, so our cell is above the top cell, then we can continue with the next index because this one is not the one we're looking for. We can do the same processing using the left or the bottom or even the right. And if we are still here, that means that we are lower than all our neighbors. So we need to increase the total by our risk factor. And that is cell plus 1. And we need to return the total value. Let's see if we have the correct value. I think the answer we're looking for is 15. We're getting 15. Let's just this. We need to log, and we need to have 4 of these. Yeah, we have 1 at 1, 2, 0 at 1, 10, 5 at 3, 3, and 5 at 5, 7. Yeah, looks like we're getting the correct values. This means we need to take a look at our input, which is a bit bigger than our initial input we tested with. We have 100 rows, and each of the 100 rows has how many? Why can I see it? It's somewhere. Yeah, I have too many things here, so I guess I cannot even see whether on which line I am. Well, I need to take care to install some extensions. I've been playing around with that a lot lately. So let's try this. Yeah, that is the input, and the first part of the result that we got in 4 milliseconds, which means very fast, is 548, and that is the correct answer. Let's see part 2, because up till now I think that we have been warming up. Next, you need to find the largest basins so you know which areas are most important to avoid. A basin is all locations that eventually flow downward to a single low point. Therefore, every low point has a basin, although some basins are very small. Locations of height 9 do not count of being in any basin, and add all other locations in order to be part of exactly one basin. Okay. The three largest basins and multiply their sizes together. So we're kinda, I'm gonna use the heck out of this. All other locations are always part of exactly one basin, because we could have a situation that means that the input, we are guaranteed by the input that we will have a string of nines. You can see it on, I will zoom it a bit. So we have a string of 9 that always cuts off any given basin. So we have this, it's better to look at it here. This, basically a string of neighboring 9s that are cutting off a basin. Otherwise, if we had a low point over here, imagine that the 3 and 4 are kind of swapped. Then we would have a low point at this point and a low point at this point, and those two low points would have shared a basin. So right now, this guarantee from the input is that all other locations will always be part of exactly one basin. So means that we actually have distinct basins in our map. So what we will need to do, we will need just to color them, so to say. And let's do that in Excel. Actually, let's start with the small input. So what I will do, I will start and color this thing. And then, is this a 9? No, color it. Is this a 9? Well, don't color it. And that's it. So I will make all the 9s black. The 9s are right now are, let's call them walls. Let's color in all the 9s in black. So we know that where the walls are. There's a 9 just about here, and I think that's it. So now, what I'm gonna do, I'm gonna take a number. So now we don't even need the numbers once we manage to write all the 9s. Actually, we can just delete everything. Colors will stay because Excel works like that. So this is our basin, and I'm gonna start from here, and I'm just gonna keep coloring. Color, color. Now what I will do, gonna use an algorithm called flat fill, so to say. So I'm coloring this thing that is not colored, and I'm writing down its neighbors that are eligible, so to say, that are not walls. That's these two neighbors. And then I go to the next neighbor and color it in. I will add all the neighbors that are still uncolored and are not walls. There's no such thing. So I will move over to the next neighbor, and that's this one, and I'm done coloring this area. And I can totally say that this area has the size 3. Next, let's say I'm just moving along. I will color this one with a different color. Let's use orange, and I'm gonna be adding this neighbor. Orange, and I'm gonna be adding these two neighbors. Color this neighbor, add this neighbor, process color this neighbor, no neighbors to add, start with this neighbor, add these two neighbors, color this, add this one, color this, and now we have a situation that we need to take care that we don't really color this one twice. But what would happen if we color it twice? It's gonna be, doesn't matter how many times we click this, it's still that color. And then we do this. We will repeat that process. Well, we're gonna start from here. Let's use light green. So we're gonna color this thing, and this thing, and this thing, and this thing. And I'm not gonna be really strict about the order that I'm coloring them. Not that color, maybe this one. But that is what will happen. Yeah. So we colored the full grid. And now we just need to say how many yellows there are, how many greens there are, how many oranges, and how many bluish gray there are. Yeah, I'm a developer. I don't understand colors. So yeah, we can do that. And in order to have that done easier, what I will do is use this trick once more for part 2 as well. But now, instead of using 99, I will just use plain old 9s. We could have used 9s earlier, but I avoided that because I wanted them to be a bit different. Larger but different, so that I can detect whether things are. So now we are treating, for the second part, the 9s are basically walls. So I will just build another wall around it. Let's print it out, so let's see how it is. Print matrix, and I actually will use this thing. If n equals 9, then print a dot. Otherwise, because we won't really care about the low points themselves, we care about the areas only, then write me an empty space. Yeah, so this is how our thing looks. And if we paste this in Excel and then do text to columns, you will be able to see that this is actually the same as it was before. Let's just do a replaced final dot and replace it with lot of x's. Replace all. So we have the yellow area here, we have the orange area here, the green area here, and the grayish blue area here. So seems that we are fine. And now we just need to run our flood fill. If we keep counting these, the levels, we don't even need to color them in different colors. We can use basically the black thingy. And I can say, while, let's go with while true, and we'll see, find a non-wall cell. We will need to find the first cell that is not a wall. And then what we will do, count it as a, not as a wall, as a area, or what was it called? Basin. Then make it into a wall. So what we will do, what I plan to do, is actually color this black. So I will say 1 and you are black, and I will count these two. 2 and you are black, 3 and you are black, and I am done. So what I've done is basically paved over a basin of size 3. Make it into a, oh no, count it as a basin, and queue all non-wall neighbors, make it into a wall. And that's all that we need to do. And find a non-wall cell. So until we basically run out of non-wall cells, because we're gonna pave through everything, we're basically gonna end up with a thing that looks like this. But we will have some data extracted from all of that. So what we want to do is find a non-wall cell, and yeah, we can do something like this. Actually, I'm gonna do a little bit of stupid code. We're gonna run through everything. Technically, this is a for loop that will go through all of the items. And if we can, yeah, it kind of learned that I did that. If cell equals 9, continue. Do I have something like that? No, that was a guess on its part. So we're gonna get the cell. Yeah, and actually I want to do exactly that. If cell equals 9, just continue. Oh, no, I want to do this. If cell does not equal 9, I'm gonna initialize it. If cell does not equal 9, the X position is the row index, the Y position is the cell column index, and break the for loop. And we're gonna need a found, because we have nested for loops, and this break will only break this for loop. Actually, I don't need a found. I can just say if X is actually -1, is not -1, then break the for loop. because we found an item. And here I'm gonna say if x is -1, then break the while loop, break the while true. So here x will be different from -1 if and only if we found a non-whole number. So that's why we don't want to go to the next row, because we already found a non-whole cell. So we're just breaking out of the for loop. And here, if we don't have a value for x, this means that we run through the whole maze and never encountered a non-whole thingy. Well, that's what it is. And I will have basins to be an array of numbers, basically. It's an array of numbers. We're gonna define a basin size that is 0 at this point. And so if we've gotten here, that means that we found a non-whole cell that is not part of any basin. So we're gonna start our basin with that. And that cell will be basically our the first cell of our basin. And now we will need to process it. So while there are cells, we will do the following algorithm. Take all its neighbors, and check. Yeah, that we don't actually need this. We already know everything about this. If the top is 9, then it's a wall. We're not doing anything. But if the top is not a 9, then we will need to add it to the cells. Yes, exactly that. So we are adding it to the cell, to the cells list. And these are all the neighbors that will need to be processed later. And of course, we need the same logic everywhere. But we don't know. Oh, we don't want to use this X and Y. We're gonna run into problems. We need to, yeah, we needed to add this. Not that. I want to do this. And we can do X and Y. Yeah. So we are overriding this X and Y, and I don't like that ever, so I will call this source X and source Y, because that's the initial point of the basin. And each time we remove a cell, we will kind of be drawing over it, so we will push that. So we are gonna say that expanded of X and Y is 9. We're gonna make it into a wall, and basin size is increased by 1. So this is this. That's that. And of course, enqueuing all non-involved neighbors is what we did with it. So while cell's length is bigger than 0, do that, and then we just need to say add the Bayesian size to all the Bayesians. For now, let's have a return 0 and just say console.log, give me the Bayesians, let me look at them. If I am correct, we should get 4 Bayesians with sizes of, let's see, 10, 3, 50 and 13. Nope. 9, 15, size 9, size 14, size 9, size 3. So we get a 1 Bayesian of size 3. And the last one of size 13, which is close enough to 14. But I don't think that's what we wanted to do. Well, one way to make sure to see what happens. Let's debug this. This -1, this is -1. The first row, the very first item is a 2, I think. Yes, it's not a 9. This is a 2, this is... Okay. If we do this, we need to break out of this for loop. So we actually got different values. 3, 11, 29, 13. The 3 part is okay. But the 9 part is... the second part is not. As I said, let's debug. We might have other issues. And that's why I like these tasks, because they always have a nice and useful intro data. So if we are able to solve the problem for the given input, the analyzed input here, it's most likely that our code will work on the first try. I rarely had a case when I managed to solve it perfectly for the example data and then had problems running with my real data. I had those kind of issues, of course, we're gonna have that, but it's few and far between. So cell equals 2. Yeah, we're gonna break it, that's not 1, so Bayesian size is 0. Cells should be 1, 1. Yep, that's our thing. X is 1, Y is 1. The top should be a 9. Yep, because we're in the corner. The left one should also be a 9. We're in the corner. The bottom one should not be a 9. It should be a 3. And the right one is a 1. Let's see, expanded of 1, 1 is 2. After this, it should be 9. Yep. And our cells array should be 2 items long. That's cool. Since it's not 0, let's shift 1. So we got the second parameter at position 2, 1. The top. And this one should be fully encompassed by 9, so we shouldn't add anything. Let's see. The Bayesian side is 2, and not cells but expanded should have 2 9s over there. 9, 1, yep. This is this neighbor that we added, the bottom one. So now we are looking at this thing, and you can see that that is also encompassed by 9s. And now cells in as an empty array. Bayesian size is 3, and that is done. Just a second, what were the basin sizes we got before? We're looking for a cell, expanded, you can see that it has all the 9s. We should have a 4. We should find these 4. Let's see if we manage to do that. Let's see, what is the source X? It should be 1. What is the source Y? It's 6. 1, 2, 0, 1, 2, 3, 4, 5, 6. Yep, that's the correct one. We found that one. The basin size is 0. That one has a single neighbor, so yep, 1, 7. That's the one next to it. So we're here. Let's uncolor all of these and let's see what happens. So right now this is inside our array and this is already a wall. So we have this case. Basin size 1. Basin size is 0. It's gonna become 1. The cells should be empty right now. We should skip the top. We should skip the left. We should add the bottom. Adding the bottom. Adding the right one. So cells has 2 items right now. Okay. I know exactly what went wrong. As I mentioned, when we're processing this thing and we're processing this thing, this cell is a neighbor both of this and of this item, and it got added on the same run twice. So when we were processing this one, it was not a wall. When we were processing this one, it was not a wall. But which means that we need to only process it once. And what I will do here is get the cell, and if cell is already a wall, that means if it was already processed, just move along, remove it from the array and don't do anything. So this means if we have the same thing enqueued more times, because for example this thing is a neighbor to 4 other non-wall entities. So when we're processing this can be enqueued. When we're processing this can be enqueued, and so on and so forth. But we don't want to count it 4 times, we want to count it once. So even if we enqueue it 4 times, we will dequeue it 4 times, but only count it once. The other 3 times it will already be counted, and we will say, okay, move along, nothing to see here. And the worst thing is that I did mention this when I was explaining the process, and then just plain forgot about it to implement it. 3, 9, 14, 9. 3, 9, 14, 9. And now find the 3 largest basins. Basins dot sort in descending order. Yep. Return basins of 0 times basins of 1 times basins of 2. Yeah, this is gonna get hard-coded. Let's see what happens now. Of course, I've just added the multiplication. I don't think that I made an error in multiplying. It's 11t34. Let's try this, and I actually gonna add the console log of the basins because I actually want to take a look at how big the basins are. Oh, we got a lot of basins. We got 200 and more. And there are some that are quite big. Is this okay? Yeah, I guess it's okay. 786048. Let's see if this is the correct value. And yes, that is the correct value. As I've mentioned, once you solve it using the example data and you are quite confident that it works for it, then most likely you have solved it in any case. Let's just remove the offending console log. We don't need that. And run it independently out of the editor so it doesn't get lagged with any debugging processing. We can see that the input is processed very fast. The runtime for the first part is also extremely fast. The second one is a bit more slow because, to be honest, this is more or less the worst way to find anything. For example, even if we are almost done, still we are starting from the top left point and going this is a wall, this is a wall, this is a wall, this is a wall until the end, and then we find not a wall and we color make 3 or 4 cells into a wall, and then we are starting from the top left corner. So this can be improved in that we don't have to start. We can start from the location of the last known, so to say, non-wall cell. For example, if we finished on 1,6 the last time, we can start with 1,7. Yeah, actually 1,7 will definitely be a wall by that time, but we can even start with 1,7 and take it from there, and we will be much faster in finding the first non-wall cells. But once more, 26 milliseconds for 100 rows of 100 items seems like a bargain. So yes, this can be optimized, and I will add a comment here. Not by using the queue, by not starting in the top left corner each time. Basically, we can continue from where we stopped. But again, if it's not too slow, we don't want to fix it, because whatever code we come up with will be a bit more complicated than this code. It's not worth the effort. We might have a code that we're going to run once and take 12 milliseconds instead of 24, so we managed to save 14 milliseconds by spending a significant amount of time on that, and by spending a significant amount of resources next time when we come in to debug it, because that code will be more complicated in general. So take care not to optimize too early, but also take care not to leave something way too slow if you can make it faster. It's always a balancing game. Most of the work we're doing in development is a balancing game. And with that, I'm gonna wish you a happy day or evening or whatever. It's evening here in Zagreb. I had a lovely time at the Advanced Technology Days conference, and greetings.